Whenever we wish to delete a node from a binary search tree, we should take care that on deleting that node, the property of the BST is not violated. And what is the property of a binary search tree? That all nodes in the left subtree, they have a value lesser than the value at the node, and all nodes in the right subtree, they have a value larger than the value at the node. So this is true for each and every node of the tree. So whenever we wish to delete a node, three situations may arise. We could have a node with 0 children. We could have a node which we want to delete which is having 1 child, or the node that we wish to delete is having 2 children. Since this is a binary tree, any node cannot have more than 2 children. So suppose, let's take this case 1, a node with 0 child. Suppose if we want to delete this node having a value 7, and this is not having any children, that means it is a leaf node. So if we want to delete this node, we simply have to remove this link with its parent node and free the space that is being occupied by this particular node, and the tree will not be affected. The properties of the BST will remain as it is. Like for this node to which it belonged, the left subtree is currently empty, but even then, even if it is having more children, we have to make sure that all the nodes on the left subtree are having values less than this, and this node is having a value which is greater than this, so it is also not violated. So we have to make sure that the BST property is not violated. What about a node with 1 child? So let's say we wish to delete this node which has 1 child. The child is 13. So if we delete this node, we simply have to remove this link with its parent. But what will happen to this node which is the child of this node n1? What we need to do is that this node n2 will now be linked to the parent node of n1. So n2 will now become a child of this node n3, and it will belong to the left subtree of the node n3. So this case is also not very difficult. We remove the link of the node that is to be deleted from its parent. We free the pointer, and its child is attached to the parent node of the node that is being deleted. We can take another case. Suppose we have to delete this node which is having a value 18. So suppose this node is n4. It is having 1 child 20 in its right subtree. If we want to delete n4, we have to break this link with its parent, and 20 will be attached to the parent node of n4. So does it violate the property? Let us see. n3 is having a value 16. So we know that if 18, which was in the right subtree of 16, it is having a value which is greater than 16. So the child of 18 would also be having a value which is greater than 18 and greater than 16 as well. So attaching it to the parent node of n4 will not change the property of the BST. Now let us see how we can delete a node which is having 2 children. So let's take another example. Suppose we want to delete this node 16, let's call it n1, and it is having 2 children, n2 and n3. So if we delete n1 and remove this link with its parent, but where do we attach the children? There are 2 children, n2 and n3, and each with its own subtrees. So how do we replace this node? How do we take care of these nodes as well? So there are 2 ways in which we can do this. N1 is having a left subtree and a right subtree. So if N1 has to be removed and N1 has 2 children, there are 2 ways we can go about it. Either we will find the max of the left subtree and replace N1 by that node, or we will find the minimum of the right subtree and replace N1 by that node. So what is the logic behind this? Now we know that in the right subtree all values have to be greater than the value at N1. So 18, 20, 19, they are all having a value which is greater than 16. So if we have to replace 16 by a node from the left subtree, it has to be the maximum, because in the left subtree all node values have to be less than the value at N1. So there are 2 things that need to be taken care of. One, that all nodes in the left subtree, they have a value which is less than the node which is replacing N1, and also all values in the right subtree are greater than the value which is replacing N1. So if we look at the left subtree, the maximum value is 13. So if we when we are removing N1 and if we replace this by a node with value 13, we still have node N2 with value 12, which is less than the node 13, and also all values in the right subtree would still be greater than this node that has replaced N1. What about node if we replace a node by the right subtree node? So we have to take the minimum of the right subtree. Why is this? Because we know that in the right subtree all values have to be greater than the node which will be replacing N1. So suppose we replace N1 by the minimum node in the right subtree, and if we search this, we find that 18 is the node which will have the minimum value. Then also 20 and 19 are larger than the value 18. So the property of BST is maintained. Moreover, the left subtree which was still having values less than 16, they would still have value less than 18 as well, because as it is 18 belonged to the right subtree. So we see that if we are having a node with 2 children and it has to be deleted, we can take either of these 2 options. In our representation of the binary search tree, we are assuming that each node is having a structure like this: struct BST node. We are assuming that it is storing integer data, and each node is having a pointer to the left child and a pointer to the right child, and each of these pointer would also be a BST node pointer. So this is very similar to the nodes that are used in linked list, and you can check my earlier videos for this. Now if we want to remove a node with 0 children, we have to remove this link that is attaching it to its parent, and we know that the address of this node which is to be removed is kept as a pointer in the parent node. So what actually we are doing is that when this node is removed, we have to make this value as null, and null indicates that the right child or the left child is empty. So anywhere the pointer is null, that indicates that there is an empty left subtree or a right subtree. Like all the leaf nodes, we see that a null value indicates that there are no left children or right children. So whenever we are deleting a node, and if we want to remove its link from the parent node, in the parent node, the appropriate pointer to that child would have to be made null. So let's see how this will happen and how we can do this using a C code. So we know that each node in our tree is of type BST node pointer, BST node, and we have the data. We have a pointer to the left child and a pointer to the right child. Now we are writing a function delete node which will take a root pointer as an input parameter, and the value, and this value is telling us the value of the node that is to be deleted. So suppose if this node has to be deleted, then a value of 8 will be passed by the calling function. This function is also going to return a node pointer kind of a parameter, because at the end of execution of this node will again return back the root pointer back to the calling function. We can either use a pointer to a pointer over here as an input parameter, and then we don't need to return anything, but to make things easier, we are returning the root value back to the calling function, and that is why we are having a struct BST node pointer as an output parameter. So the logic behind this code is that this value that is received over here will be compared with the root data. If it is less than the root data, then we know we have to traverse the left subtree, because that is the property of the binary search tree. And if it is greater than the value at the root node, then we know we have to traverse the right subtree. And this we are going to check at each and every node. So let's proceed. We know that we have received the root pointer value, which is 200 over here. 200 is the address of the root node, and this is accessible through a root pointer. So this is a root pointer which is giving us the address of the root node, and currently it is having a value 200. So we have reached the root node, and now we will start our code. First of all, we will check, is root null? If the root is null, that means the tree is empty, and in that case we will simply return the root back to the calling function. Here our tree is not empty, so we come to the next statement, which is a condition to check whether the value is less than root data or not. Our value is 8, root data is 10, so that means our value is less, so we have to traverse the left subtree. Now if we have to traverse the left subtree, we will have to give the address of the left child, and this address is available in the left pointer of the root node. So we will pass on this address, and there will be another call to this function. So it is a recursive call, and now root arrow left, which is giving us the pointer to the left child, it will be sent as a parameter to this function. And whenever this function is going to return, it will be collected, the root that will be returned, it will be collected in root arrow left. So whenever this function returns back to the root node, the root value that is being returned will be collected in the root arrow left of the root node. So now we know that there is another root call to this delete node function, and 300 has been passed to this function now. Again we will check root is null or not. No, it is not. We will check, is value less than root arrow data? No. This condition is also not satisfied. So we come to the next statement. Is our value greater than root arrow data? Yes, our value is 8 and it is greater than the root arrow data. Right now root is 300. It's having a value 300. So if it is greater than the root data, that means we have to traverse in the right direction, right subtree now. So we have to go in this direction. So to go to the right child, we need to send the pointer of the right child, which is this 350, because the right child is at address 350. So now there will be again a call to this function delete node, and now we will send the root arrow right value, and whenever this function will return, it will be collected, the return parameter will be collected in root arrow right. So now there is another call to the function, and we will send 350 address to the function. So another call to the delete node function, 350 has been sent. Again we will check, is root null or not? No, it's not true. Is value less than root arrow data, value is 8, root arrow data is 6, so no. Is value greater than root arrow data? Yes, again, so again a call to the function, and now this pointer 500 will be passed to the delete node function. So now we are going to have 500 which will be passed to this function again now. Now we are at this node, okay. So again we will check, root is null, no. Is value less than root arrow data? No, because we have reached here, our value is 8 and the root data is also 8. Is value greater than root data? No. So then we have to, now that means we have reached the node that is to be deleted, and now we need to check whether this particular node that is to be deleted is having 0 children, it is having 1 child, or it is having 2 children. And how can we check that? By checking its left and right pointers. If both the pointers are null, that means it is having 0 children. If only one is null, that means it has 1 child. And if both are having some values, both are not null, that means it is a node with 2 children, and now we have to proceed accordingly. Here we know that both the left and the right child pointers, they are null. So we are coming to this statement, if root arrow left is equal to root arrow right is equal to null. So what we have to do is, that means we have reached a child node over here, and in this case if it is a child node, what are we supposed to do? We have to simply break this link and free the space that was being occupied by this particular node. So what we will do is free root. Root is currently having a value 500. So whatever was the space that was being occupied by this node at address 500, that is going to be freed. Now we are going to make the value of root equal to null. Why is this? Because now when we will return root, a null value will be returned and it will be collected over here. So now we know that this node is no longer having a child, so this link that was there will be broken. So we make root equal to null and we return root. So when we return from this function, it is collected over here and we get a null value over here. And this node has been freed by this statement. Now when we are back over here, this function will also return, and it will return a value 350 over here, because the root value for this node was 350. So 350 will be collected back here. This, when it returns, it will return a value of the root which is 300, which will be collected over here. So as you see, only the parent of the node that was deleted, only that is being changed. The value of that particular node pointers are being changed. Other nodes are not being affected. Now suppose the calling function had sent in a value of 3. So we know that this node is the one that is to be deleted. This is a node with 1 child. How can we know that a node is having a 1 child? One of the pointers would be null. Even so, if this is having a left child, so the right pointer is null. This is having a right child, so the left pointer is null. So we know how to come to this node. We know how we can reach this node from the root node by recursive calls. So once we have reached here, now we have to delete this node. When we have to delete this node, we have to take care of its child. And what we have to do is, we have discussed this earlier, that this node needs to be assigned to the parent of the node that is being deleted. Suppose N3 was the node that is being deleted. So N4 will be assigned to node N2. So N2 will become the parent of node N4. So if the address of N4 is suppose 700, then this value which was currently pointing at node N3, it needs to be changed to 700 to point to node N4. So these are the changes that are required. So we know that by recursive calls we have reached node N3, and what we are going to do is, so we are done with recursive calls, we are done with this part, and we have come here where we are having the value of the node that was passed into the function. Is root arrow left is equal to root arrow right equal to null? No, this condition is not satisfied. So we'll come here. Is root arrow left equal to null? No, root arrow left is not equal to null in this case. Now we come to the next condition. Is root arrow right equal to null? Yes, root arrow right of node n3 is null because it is having only a left child. So now what we will do is, we will have a temp which is again a node pointer, and in this temp pointer we will put the value of the root, which is 400. Why is this? Because we want to free up this space. So we will put up this value over here in the temp pointer. Now we are going to change the value of the root. Currently our root is having a value of 400. This because we are currently at node n3. Now we are going to change this to point to root arrow left, because now we want to put this value over here. Suppose, so this value was 450, sorry, this is 450. So in this root we are now going to put a value of 450, which is now pointing to the node n4, which is the child of node n3. And now we are freeing up the temp, that means the node at 400. So all that space that was allocated to this node at 400, this n3 node, this is going to be freed up, and we have to return this value 450 to the parent node n2. So when we will do return root, this root value 450 will be returned to n2 and will be collected over here. So this will become 450. And when this function will return, it is going to return whatever was the root value. There will be no changes there. So this is how a node with one child will be deleted. Similarly, you can check that suppose if value 6 was being passed over here and you reach this node with recursive calls, we will be ultimately coming to this point where root arrow left will be null, because now there is no left child, there is only a right child, and in that case again, when this node is deleted, this will be assigned to the parent of this node, and a value of 500 will be sent back to this calling function. So these statements, temp pointer will point to root, which will have the value 350 so that it can be freed up. Root will be equal to root arrow right, which is 500, and this 500 will be returned back to the calling function. So 500 will be received by this node n2 in its root arrow left pointer. Now suppose if we have to delete a node which is having 2 children, then how will we proceed? So suppose the value that is being passed by the calling function is 4. That means we want to delete a node which is having this data 4. This is this node. We want to delete this node, and we can see that this node has 2 children. The left subtree is being pointed to by the pointer 400 and the right subtree is being pointed to by the pointer 350. So if we start calling this function, and if this function starts executing, from the root pointer we will reach this node. Let us call this node n2. And what we are going to do is that we are going to replace this node, as I discussed earlier, by the minimum node value in the right subtree. Okay. So we have done all these parts and we have come to node n2, and now we are over here. So here, since this node is having 2 children, we are at this statement. Here the left child and right child both are existing. So what we are going to do is we are going to write another function which will find the minimum value in the right subtree. So we are going to pass this right pointer 350 and in this right subtree we will find the node which is having the least data value. So we know that this least data value is over here at node, let's call it N3, and we know that 6 is less than 8. So this node N2 we are going to replace by node N3. And how will we do that? Let's see. So the first thing we do is, after we have found the node with the minimum value, we replace the root data. Root is currently this 300. So we replace this root data by the data of the node which is pointing to the minimum value. So temp is pointing to node N3. Temp is pointing to this node which is having value 350. The address of this node is 350. And the data of this temp pointer is 6. So root data, this we are going to replace by 6. So this data becomes 6. Now what we are going to do is, we have actually replaced N2 by N3. Only thing that we need to do now is we need to assign this child to N2 and we will be done. Now we can delete this node N3, and whatever were the right children of N3 or the left children of N3, they will be transferred back to N2, which has now been replaced by this data value of N3. And again the same process, same recursion will start, where root arrow right, deleting of 350, the node at 350 will start, and we will pass on the value temp arrow data, which is 6 now, so that this node N3 is deleted. We have already replaced 6 in the node value of N2. So this is how N2 will be replaced by N3. It is simply putting this value of N3 into this value over here and deleting this node, assigning this node to the parent node. So this is how a node with 2 children would be deleted. So in essence, you have deleted N2 by simply transferring N3 data to that address 300.